Hi everyone! Today we are going to talk about what makes a relation a function and an inverse function. In this video, you are going to learn how to be able to determine whether a relation is a function using lots of different representations. We're going to look at graphs and use the vertical line test. We are going to look at sets of ordered pairs, tables of values, and also maps. Once we get comfortable with functions, we are going to talk a little bit about inverse functions. Specifically, we are going to be looking at how they are a reflection over the line y is equal to x, and we are also going to use the horizontal line test so we can tell if an original relation's inverse is a function or not. So let's get started. The first thing that we need to talk about is relations themselves. A relation is just a set of ordered pairs. You might see the ordered pairs represented as ordered pairs. They might be drawn in a table like the second picture. You could have the ordered pairs plotted on a coordinate plane, or you could have a map where you have all of the input values in one shape, all of the output values in another, and the arrows mapping in between tell you which input values go with which output values. So this first one, for example, -2 maps to -2. That means the ordered pair -2, -2 is in this relation. When we talk about relations, there is a little bit of vocabulary that you need to know: domain and range. The domain of a relation is just all of the first elements in the ordered pairs, or all of the x values. So if we look at this set of ordered pairs, this relation, let's write down the set of numbers that are in the domain. I drew these squiggly brackets because they mean I'm looking at the set of something. If I look at my x values, I see that I have -2, -2, 0, and 3. I don't need to write that -2 two times. I'm just going to write it once: -2, 0, and 3. Notice that there are commas in between each items in the set. You must have those commas to delineate the three numbers in the set. -203 is not in the set. That's what it would say without those commas. The range is the second element in each of the ordered pairs. We also call these the y values a lot of times. We can write the set that is the range of a relation the same way that we write domain, where we list out all of the numbers 2, -2, 1, and 1 without repeating. And I do want to note that we are going to write them from least to greatest, left to right. So rather than starting with 2, I'm going to start with -2 because that one is the smallest. Then I'm going to say 1. I'm not going to say 1 again because that's a duplicate, and then I'm going to go back to that +2. Alright, so let's look at functions now. The definition of a function is if you have a relation, like we have here in this example, and each input value, or the domain of that relation, maps each input to only one output value, or one value in the range of the function. So notice that for each of the input values in the domain, there's only one arrow coming off of each of those values. That's what makes this a function. You cannot have two arrows coming from the same number. If that were to happen, this would not be a function. Each domain value only gets one range value. All right, so let's look at a graph now rather than a map or a table or a set of ordered pairs. If we're looking at a graph and we want to determine if that relation is a function or not, we can use the vertical line test. The vertical line test says that a relation is a function if and only if that vertical line only touches the relation at one point. Always. So if we take this vertical line and we put it on our function or our relation, it only hits there, that ordered pair. If we were to move it over to the left, over here, it would still only hit at one point. If we were to move it over again, way over, it would only hit at that one point. So because it only touches the graph at one ordered pair all along this relation, no matter where I put the vertical line, that means that yes, this is a function. Now, if you look at the second graph that says not a function, the problem with this relation is if I have my vertical line and I'm looking at where it hits the graph, it hits at 2 places. That means this is not a function because the domain, the x values, repeat. It fails the vertical line test because it hits at 2 points. Now you'll notice with this one there are many points where it fails the vertical line test. If you wanted to give an example of it failing the vertical line test, you could say that it failed at any of these x values. So I could say that x is equal to 1 is a place that it failed. I could say x is equal to 2, x is equal to 3.5. Any value where it fails is a good example to give to show that it is not a function. All right, let's do some practice. In this first one, we're given a table and we're asked to figure out domain range and whether or not it's a function. Remember, the domain is the x values, so I'm going to write this in set notation and just list out all of the x values. 1, 2, 3, and 4. The range is all of the y values, so I'm going to list out all of my y values without repeating anything, which means I'm just listing 5 and 10. Now, in order to be a function, remember that for each input value, each x, it has to only go to 1. So that means if I'm using 1 in this row, I can't find a 1 later down in the table. 1 is not repeated, 2, 3, 4. None of those are repeated. So yes, this is a function because the domain does not repeat. If I look at the second one, the domain is all of the input values, so that's -3, -1, 1, and 2. The range is all of the output values, so that's 2, 4, and 5. And I'm looking at a map, so to determine if it's a function or not, I want to look at the domain and look at the arrows. For each number in the domain, is there only one arrow mapping it to something? The answer is yes, there's only one. So yes, this is a function. The domain does not repeat. What would have happened if my map had an arrow going from -3 to 4 in addition to the other 2 arrows? Well, that would mean that this is not a function because at x is equal to -3, the domain would repeat. In that case, I would have circled no for not a function. Luckily though, that's not what our question asked us because our map, that was what our question asked us, but the map did not show that. There was no arrow there, and so we could say yes, it was a function. All right, so let's look at some graphs now. Remember, when you have a graph, you want to use the vertical line test. So if I draw a vertical line, does it only hit, that was a bad vertical line, sorry. Does it only hit at 1 point? Yes, it does. If I draw another one, does it only hit at 1 point? Yes. What about another one? All the way down, it's only going to hit at 1 point the whole way. So what does that mean? It means that yes, this is a function. And because my directions ask me to explain my answer, I'm going to say that it passes the vertical line test. Now, I could also say for this one that it's a function because the domain does not repeat. Either of those are perfectly fine explanations. All right, let's look at the second one. Is it a function using the vertical line test? Let's draw a line. How many places does it intersect the graph? At 2. That means this one is not a function. It's not a function because it fails the vertical line test. You could also say that the domain repeats as an explanation. it repeats because if we look at these ordered pairs, that's -2 is the x value for two different ordered pairs. It is at, what is that, like 1.5 maybe, at -2, 1.5, and down at -2, -1. All right, let's take a second to look at this last one. Using the vertical line test, does this relation, can we classify it as a function? The answer is no, of course not, because it fails the vertical line test. When we draw a vertical line, it hits the graph at two places. You can also, of course, say that the domain repeats. All right, let's move on now and talk about inverse functions. Inverse functions are functions that take an original relation's output values, and when they map those output values as their input, you get back the original relation's input values. Now I know that sounds complicated, but really all that's happening is that the domain and range are switching places. If we look at a graph, we're going to see a reflection over the line y is equal to x, and we'll look at that in a moment. So let's look at a table and a map first. You're given a table for this original relation. Let's go ahead and draw that as a map. So let's put the x values in our domain, and let's put the y values over here in our range. And then let's map, meaning let's draw all of the arrows. So -1 goes to 2, 0, 0, 1, -2, and 2, -4. Now with that map drawn, I'm going to skip over here to the inverse relation, and let's go ahead and draw this map as well. So my input values are going to be my x's, 2, 0, -2, -4, and my output values are going to be my y values, -1, 0, 1, and 2. So let's map it, drawing those arrows. Do you notice anything about the numbers that we just drew in these two maps? Did you notice as you were writing that the range of the original function got moved over to be the domain of the inverse relation, and that the output values over here, the range, were exactly the same thing that we started with as our x values in the original relation? This is what an inverse relation is. It takes the x values and the y values and it swaps them. The x values become the y values from before, and the y values, the range, is the same as my original domain was. It just flips them over. So let's look at a graph. First, let's plot all of these points so we can see what it looks like graphically, and then we're going to find the inverses. So we're going to plot 0, 0, 1, 2, 2, 4, 3, 6, and 4, 8. All right, so we plotted all of those. Now I'm going to change my color here just so this is a little bit easier to see. Let's do their inverses now. Remember, we just talked about inverses are when all of the things that in the x's flip to be in the y's and vice versa. So we're just going to write a list of ordered pairs where we flip all of these values. We're going to flip 0, 0. It's not going to change much. It's still going to be 0, 0. But this one, 1, 2, is going to become 2, 1. 2, 4 becomes 4, 2. And so on. 6, 3, and 8, 4. All I've done was flip the x's and y's, or interchanged them. Now if I plot all of these points, 0, 0 is still there. Then you've got 2, 1, 4, 2, 6, 3, and 8, 4. All right, so we have our two graphs, and it looks like these sets of ordered pairs are kind of moving or reflecting. So let's draw in, I'm going to change my color one more time, the line y is equal to x, because that's going to be our line of reflection. Y is equal to x is that point that starts at the origin and then rises 1 and runs 1, rises 1 and runs 1, all the way up. And it goes all the way to the left as well, falling and running to the left. So that gives me this line of reflection. And it looks an awful lot like if I were to take this graph on my paper and fold it up where the crease was that green line, those red dots and those blue dots would match up perfectly. It would be like a mirror image. So that means that we do have an inverse here. Whenever the paper folds up like that, it means that the graphs are inverses. Now the question that I'm being asked here is not are these inverses, but is the inverse itself a function? So if I look at the inverse, meaning the blue ordered pairs, to find if it's a function, I'm using the vertical line test because I've got a graph. So if I look just at the blue ones, for every x value, if I were to draw a vertical line, does it only hit the blue graph at one point? The answer is yes, it passes the vertical line test. Now, you also could say here, by looking at either the graph or at the ordered pairs that are in blue, that the domain does not repeat. Because each x value is only listed one time. 0, 2, 4, 6, 8. None of those numbers repeat in the x value position. All right, now there is an easier way with graphing to determine if the inverse of an equation or a relation is a function. And to do that, we're going to use the horizontal line test. The horizontal line test is really similar to the vertical line test. You are going to take an original function, not one that you flipped points on to look at the inverse, but the original function, and draw a horizontal line. If the horizontal line only hits the graph at one point, then it's going to be a function. So let's look at this example. First, we want to know, is the graph a function? Now that is not talking about inverses, that's just talking about the graph as it is. So that means we're going to be using the vertical line test because we're looking at the original. If I draw on a bunch of vertical lines, notice that for all of these, it only hits at one point. That means that this is a function, and it is because it passes the vertical line test. You could also say that the domain does not repeat. All right, so now if we want to look at the inverse, I'm going to switch back to my blue color. We're still going to look at this original graph, but this time we're going to use a different test, the horizontal line test. Using the horizontal line test, if we draw a straight line across at any point we want, we're looking for, does it hit at one point or does it hit at two? And unfortunately, it hits at multiple points on the horizontal lines that I've drawn. It hits at 2 at the top one, it hits at 3 on the middle line I drew, and it hits at 2 again at the third bottom line that I draw. That means that the inverse is not a function because it fails the horizontal line test. You could also say here that the domain repeats, because for the inverse, it does repeat. All right, so let's do one last piece of practice now. This time we are going to use our calculator to do some graphing and help us out. So I'm going to pull my calculator up here and we are going to write down the steps kind of as we go. So I need to graph both functions and then figure out, are these inverses of one another? So in order to graph this function in the calculator, I first am going to go to the y equals, I'm going to hit the y equals button, and then I'm going to enter in the rule of the equation, not the name of the function f, just the rule. So I'm going to put in 2x plus 3. So in my calculator, I'm going to hit 2, and then this button here is my x plus 3. Then I'm going to hit the down arrow because I have 2 functions to input. And then I'm going to input my second function into the y2. And that one was 1/2. Oh goodness. There we go. 1/2, which I'm going to do in parentheses, x minus, and then in parentheses again, 3/2. So in that y2, I've got my first parenthesis, 1 divided by 2, in parenthesis x, minus, and then in parentheses I have that 3 divided by 2 for that second fraction. Now after I have those in, I'm going to hit the graph button, and that's going to take me to a picture of what those 2 lines look like. Oops. Now you can eyeball it, but it's hard to draw a graph looking at something like that. So instead, I'm going to hit second table, which is going to take me into a list of ordered pairs that's going to be much easier to draw my graph from, since I have to draw a nice graph as well. Okay, so looking at this table, I'm going to put my f of x, y1 in first, so 0, 3 is there, and I'm going to pick pretty points here. 1, 5 is nice, 2, 7 is nice, 3, 9 is nice. I can go up if I want to go the other way, so that's -1 is up at +1. Oops. And, oh goodness, let's get back there. There it is. Okay. So at -1, I'm up at +1. And at -2, I'm down at -1. All right, so this is my line f of x. And then I'm going to switch my color to red, just so it's nice and easy to see again. And I'm going to do nice points from the second one. So I'm going to pick -1, -2, and 1, -1, and 3, 0, and 5, 1, and 7, 2. Alright, so I think that will give me enough to be a nice line. Alright, so that is g of x. I've used my calculator to graph both. Alright, and now I want to determine if they're inverses. The table is going to help me with that determination. So when I look at my table, remember you're looking for the values to flip-flop, meaning if I look at these values to start with, I want them to flip my output values to be my input values here, because then those match back to the beginning. So at -4, my original function, the blue one, was at -5, at -2 it was -1, at 0 it was 3, and at 2 it was 7. Alright, so now I'm going to look at my red function, and this time I'm going to look at the y values to figure out what the x values are. So I'm looking at first where the function is -4 in the red column here. So I'm going to scroll up a little bit. And at -4, I see that the x value is -5. That looks good because it matches. If I look at -2, that's down here, the x value is -1. So that's good. At 0, it's 3. And at 2, I've got to scroll down. it is, oh goodness, we're too far. There we go. At 2, it is 7. That means then, because this interchange worked, it flipped, that means that yes, these graphs are inverses. All right, so now with all of that, we have talked about how you can look at a relation and figure out if it's a function. If it's a graph, you use the vertical line test. You can look at the ordered pairs table of values and maps just by looking at the x values to see if any of them repeat. We can look at a graph and figure out if the inverse is a function, either by thinking about the line of reflection or by thinking about the horizontal line test. And we can also look at the table like we did in that last one so that we can figure out if two equations are indeed inverses of one another. That wraps up our lesson for today. So we will pause here.